Hey friends, I've come your way again and we have something to talk about. Okay, so today's presentation will be on hunting for prime numbers using multiple threads, the P thread, the pulses thread. All right. Um, so let's get into that. So imagine we have eight treasure hunters searching for rare treasures or gems, let me say gems, across a massive landscape. And they need to find exactly 50 gems. So eight treasure hunters searching for rare gems across a massive landscape, and they have to find exactly 50 gems. No more, no less. How do they coordinate? How do they stop? Or how do they know when to stop? Right. So that is what we're talking about today. And think about that. Imagine that. So this is exactly the challenge we solved with our prime number generator. So our power prime number generator. That's exactly the challenge we are solving with that. Okay. So I have my code here right here. Okay, so before that, let me exit right here. Okay, so this is my terminal. And this is the editor. All right, so here we need to include all the libraries we need. And we do our configuration settings where we have to define the number of threads. Again, it's treasure hunting, right? And then we have to define the number of values or the number of gems we are looking for, which are 50 total prime numbers to look at. And then maximum random value, upper bound for random number, right? Okay. Now, don't forget, we have to do a global shared data. So we have this right here. And um, we have our synchronization primitives. So here, that's our core architecture. Um, this first one is the bouncer. Okay. So again, let me change the story a bit. So imagine we go to a club and then we have a bouncer. So the bouncer here is trying to control crowd, right? So the P thread mutex T collection mutex is our bouncer, and the P thread, second one, I mean, is the way of communicating, the walkie-talkie, the means of communicating to other. All right. Okay. Now let's keep going. Okay. And right here, we want to check our prime number function. So we are checking to see if a number is prime using optimized trial division. So here we are using this method right here. And then we are giving it two conditions that if the number is less than or equal to 2, then it should return a false solution. So here, basically, prime numbers start from 2. So numbers below 2, no negatives, 1, 0, and a prime number. Right? Again, if the number is equal to 2, it should return 2. Yes, 2 is a prime number. And here, we are saying that if the number is equal to 0, we should return 4 because the prime number is not 0. And then now, this is the main part. This is the main part. So basically, this is where the real work begins. So we we here, right, for the unsigned long division. So here we divide by 3, right? And then the divisor by divisor. Yeah. So we take this part into consideration. But yes. And then if the number is equal to 0, we make it a false. So we say that we skip even numbers after 2, definitely. We skip even numbers. So right here, we're skipping the even numbers after 2. And we only check devices up to the square root. So right here, we're checking devices up to the square root. So this makes our plan testing incredibly efficient. But here's the key insights. This function is thread safe. It uses only local variables. So multiple threads can run it simultaneously without any coordination needed. Right. Okay. Now let's go to our prime number handles, our worker threads. So that is this next part. So here, the worker function for each thread collaboratively hands for prime numbers. So here, all 8 threads are going to transfer the gems, right? So right here, We are collaborating. We are working together. So each worker thread follows this pattern. First, it politely asks or checks if the expedition is complete. Notice we use a mutex for this check. That's very crucial. Okay, use a mutex right here to check if it's very if the expedition is complete. Then it generates a random number and tells its prime. If it finds one, it calls our synchronized function to safely add it to the collection. So if we find one gem or one treasure, we add it to the collection. So the small delay prevents it beyond them because it's an low playing system. Okay, so let's keep going. Now the critical moment when adding all of this here, this part is check if we've collected enough primes, and here we generate and test a candidate's number. We generate and test a random number for students. And then this where if it's a prime number, we add it to the collection, right? And then we double check condition after acquiring the lock, the mutex lock. And right here, we check if we've reached the targets. Okay. And this is just to say that small delays to prevent the harming mutex. Right. Okay. And let's go to the main program. The main program. Okay. Go to the main program. So here, this is the master's main responsibilities. All right. So to start with, we just a moment. So here we have the int name. All right. And so we start the whole thing. And we have a COUT right here. And then so we start the timing. And now we initialize set collection. We launch the wake up threads. So this is where we launch the wake up threads. And the master thread waits for the completion, right? And here we cancel all the wake up threads. We wait for all threads to complete. We stop the timing here. And we display our results. So here, it's all about result display, right? So we display all the collected prime numbers. And then here we verify all numbers are actually prime. Like this is just verification. And then we do a cleanup and return the solution. Okay. So the master thread is brilliant in its simplicity. Instead of constantly checking, are we there yet? Like an impatient child. It goes to sleep with the P thread conway. Right. So this function releases a mutex and sleeps until the webpack thread signals that we reach our target. This saves CPU cycles and is incredibly efficient. When awakened, it systematically cancels all webpack threads and cleans up resources. Okay. Okay. So now let's run this. And there we go. Now we see some action. Boom. So let me start from here. So from this solution, these are our solution. So this is the displayed result. So what target prime numbers? We are looking for 50 gems, and we are using 8 treasure hunters. The maximum number of values is not a big number, right? So this is how we launch the 8 work threads, and we start by hunting. Okay. And try 3, try 4, try 5, 6, yeah, depends. Master thread waiting for all of them with 50 primes by starting time terms. Okay. So this is all about it. So each is checking to see if they are and target of 50 primes reached. Signaling all threads to terminate because we are looking for exactly 50, no more, no less. Right. Okay. So these are the prime numbers that's where it got right here. Okay. All the 50, it's counted them for us. Okay. And verification is that all numbers are prime. Now, let me so with this, we can see that 8 people or 8 treasure hunters are looking for 50 gems, right? 8 treasure hunter looking for 50 gems. So let's assume we just have one treasure hunter looking for 50 gems. The time it will take for that treasure hunter to find all 50 gems will be a lot, right? And then how about two? Two is better than one, they say. Yes, so the time will reduce. Or increase it to four and then to eight. The time to take when finding this gems will definitely reduce significantly. Right. Yeah. So the efficiency with the efficiency, um the results are so beautiful. So with two threads, we get a 1.86 times speed up. That's 93% efficiency. With four threads, we are still at 85% efficiency. But with eight threads, coordination is difficult, right? So coordination cost is visible. So that increases the speed time. Yes, you'll find it quickly. Yes, but efficiency will reduce. Not to succeed. Why? Because our single mutex becomes a bottleneck. Too many threads waiting in line at our digital doorway. So this perfectly demonstrates Amdahl's laws, which states that the sequential coordination paths limits our maximum speed up. All right. So you can see that the real-time coordination each thread announces when it finds a prime number. And the moment we hit 50, everything gracefully stops. So what are our key takeaways? What have we demonstrated today? So we demonstrated that synchronization pattern that scale from two to dozens of threads. We've demonstrated synchronization patterns that scale from two to dozens of threads. And we have also demonstrated efficient coordination using condition variables instead of busy waiting. Third thing we demonstrated is real performance insight about the costs of synchronization and a production-ready code with proper error handling. These patterns aren't just academic, they are using web servers, databases, game engines, and scientific computing, everything. And so, we have shown how tightly coordination turns individual computational effort into an efficient team and power programming as in life. Teamwork makes the dream work. Right. So if you have any questions, you can drop it in the chat and I'll be happy to answer your questions. Have a good one.